Hello and welcome to UCL Physics Tutorials. In today's video, we'll be introducing the basic concepts of crystal lattice structures, closely following the first year undergraduate course material from Thermal Physics Part 2. In order to understand crystal lattice structures, some basic concepts must be firstly defined. Let's start with the lattice. A lattice is simply a regular arrangement of points in three-dimensional space, such that the environment of every point within the structure is identical. Every point can be represented as a set of linearly independent vectors, such as the set of perpendicular unit vectors along the x, y, and z axes. As a result of this very general description, lattices can be found in naturally occurring structures, such as beehives.
If we want to make a lattice out of this 2D beehive, we need to start by choosing an arbitrary reference point, like this one, and examine its environment. After we've chosen our point, we just need to choose every other point on the beehive that has an identical surrounding to our first point. If you look closely, the second point that we just added does not share the same surrounding as the first point, and therefore it's not a lattice point. Let's remove this one for now and fill the lattice the way it should be.
Notice that each lattice point has the same surrounding area, revealing the points of symmetry in the beehive. Crystals and many other structures can be described using lattices. By substituting some or all of these points in space with atoms or groups of atoms, or symmetrically placing these physical objects between lattice points, a crystal lattice structure is formed. Due to the difficulty in differentiating between different lattice structures, a simplified description of crystal lattice structures is required. For this very reason, chemists and physicists have come up with a definition of the unit cell, which is a parallelepiped in 3D, as you see here, or a parallelogram in 2D, whose vertices are lattice points and from which an entire lattice can be built upon by repetition in all of the allowed dimensions. Basically, they help reveal the structure of the lattice using geometrical objects, so that we don't have to work with a myriad of lattice points. Here, in this 3D lattice, a primitive unit cell is shown. Highlighted are the 8 lattice points that connect the cell. The reason we call it primitive is because it only contains a single lattice point. Now, this might seem confusing because there are clearly 8 highlighted points shown. We'll talk more about this later, but the reason is because each point on the vertices only contribute to 1/8 of a lattice point, adding up to a total of 1. Here's an example of a non-primitive unit cell. We can easily tell this by noticing that it contains lattice points on the sides of the cell connecting it, making the total amount of lattice points in the unit cell equal to 2, as the lattice points on the sides each contribute to 1/4 of a lattice point.
Let's go back to the 2D lattice to simplify things. Here we can see the unit cell highlighted with green lattice points. What is it that makes us choose this particular parallelogram as our unit cell? It is generally possible to choose it to be any parallelogram, but in practice it is best to choose the smallest possible unit cell as we've done here. For some lattices, the smallest unit cell fails to describe the symmetry in the lattice. In these cases, it is preferable to find a larger one that can describe the symmetry. This larger unit cell does a better job of showing the symmetry in the lattice, as you can see here. But in the cases where there is an angle of 120 degrees between the lattice points, it is best to use a hexagonal primitive unit cell, like this one, which shows a 6-fold symmetry. Let's take a closer look at the different types of unit cells that we usually find in lattices. The simplest unit cell is a simple cubic cell. It consists of 8 lattice points positioned in each corner of the cell. How do we know how many lattice points a unit cell contains in total? We can calculate this by adding up the contribution of each lattice point in a unit cell to the total. For this unit cell, a lattice point in a corner makes up 1/8 of a whole point, because it's shared amongst 8 other unit cells. A point on this side makes up 1/4, a point on the face 1/2, and lastly, a point entirely within a unit cell is a whole lattice point. If we count the points of the simple cubic unit cell, we see that in total it contains 1 lattice point. Here we see the body-centered cubic cell. It's similar to the simple cubic cell, except that it has a point located in the center as well. Counting the point on the vertices and the point in the center, we see that the cell contains 2 whole lattice points. The face-centered cubic unit cell is composed of 14 points, 8 at the vertices and 6 at the face centers. Counting the point on the vertices and the ones on the faces, we see that the cell contains 4 whole lattice points. Finally, I'll quickly go through the geometry of the unit cell, namely lattice parameters. The geometry of the unit cell in 3 dimensions is defined by a right-handed set of crystallographic axes, x, y, and z, that point along the edges of the unit cell. A complete description of the structure of the unit cell is described by its lattice parameters. These parameters are the lengths of the unit cell along the axes, seen here as A, B, and C, as well as the angles between these lengths. Highlighted here is A, with the angle alpha between B and C. Here is B, with angle beta between A and C. Here is the angle gamma between A and B. That concludes our introduction to lattices. There's a lot more material to cover, but we hope that our video helped you to understand some of the initial concepts. Thank you for watching this episode of UCL Physics Tutorials. If you liked what you saw, please click like and feel free to ask any questions in the comment section below. Thank you.